exactly the same. It's basically exactly the same as on the other side, just now the let's say the magnet and the cooling is much more powerful. So basically we can go down to 8 millikelvin. So 8 we can really cool the sample down and look make sure that the thermal occupation at terahertz frequency is really
But materials is the same here.
Yes, the materials will be the same, but it opens up new possibilities if you, because there we can, I think we can go down to roughly 1.5 Kelvin or so, but yeah, below 1 Kelvin many new interesting things can be seen. So our hope is that with this new magnet and new dilution fridge we can see new effects.
Are you looking to have very powerful terahertz radiation or?
No, not really, not necessarily. We are looking to have very good detection, so that's why we are very interested in the zinc telluride crystal itself, and somehow engineer the crystal, because I mean the detection technique is based on electro-optic sampling, right? So meaning you use the Pockels effect inside the zinc telluride crystal to detect terahertz transients, and the Pockels effect is basically linear in electric field. So that means that if you manage to somehow enhance the electric field inside the zinc telluride crystal, this effect will be bigger. So even though free space the electric field will be the same, so you have the same sample, but if you, for instance, manage to put the zinc telluride crystal inside the waveguide or so, then the electric field of the wave which will be coupled in will be much more enhanced, such that the Pockels effect will be bigger. So now one of our ideas would be, for instance, to try to do waveguides on zinc telluride crystal, terahertz waveguides, which doesn't mean much. It means just that to be able to make zinc telluride crystals which are rather thin, so close to the wavelength, and for the terahertz maybe 100 micron or so wavelengths in free space, and then with the refractive index of zinc telluride maybe of something like 30 micron thin crystals, and such that we come with a terahertz inside this crystal, and together with the IR we like this we managed to.
You need something to couple terahertz.
Yes, exactly. And yeah, and then we could put something like a horn antenna or something to couple the terahertz efficiently into the terahertz waveguide, which has as a core the zinc telluride crystal, and like this enhance the Pockels effect. Because so far, I mean, probably you know, the crystals that we buy are typically 1 by 1 centimeter, and then they have a certain thickness, maybe 1 or 2, 3 millimeters or so, and yeah, so basically it is a bit as free space. So the terahertz wave is not very well focused, is not very collimated, and this is also one thing that we hope to achieve by waveguiding, to have a wave which is collimated over a longer length, and yeah, and have it much more, have the electric field much more enhanced by confinement, basically. Yeah, so you see this is one of your crystals, for instance. Yes. Yeah, so basically, but this is all done in Terahertz Time Domain Spectroscopy.